Hi everyone, welcome back to today's math channel. I'm your host David Tare, and this is my third video in my sub-series of calculus on derivatives. And today I'm going to talk about the linearity of the derivative, which I've written out on the middle of this slide. I'll go over this in a minute, so don't worry about this right yet. But anyway, let's begin. And I just want to give you a little bit of overview of where we're going and where we've been. So far, I think I've only derived one rule for differentiation. That was in the last view I made yesterday. So we derived the power rule. That's the one with a solid green dot on the left. The derivative of x to the alpha is alpha times x to the alpha minus 1. We didn't really derive this in its full glory. Alpha is supposed to be arbitrary in this formula. I guess it could be an arbitrary real or even an arbitrary complex number, but we proved it for when alpha is a non-negative integer. That's enough for us right now. I think later we'll do more general versions of the power rule, but anyway, this is done. And then the ones I'm showing here with a hollow green circle are the ones I'm going to do today in this video. And we actually can kill two birds, or actually three birds with one stone here, because linearity, it turns out, is a very general rule. And as consequences, very simple consequences of linearity, we get two other rules for free. We get the sum rule, which is the second rule on this slide. Um, and we also get the rule for multiplication by a constant, also known as the scalar multiplication rule. So those will come out for free once we get linearity. The only one on this slide we're not going to do today is the product rule. This is also called Leibniz's rule. This is a very important rule, but it's a little bit harder to derive. I'm going to do that in a future video, probably my next video. So that's why this is in red. But anyway, that's just kind of an overview of where we're going and what we're going to do today. And now let me just spell out explicitly what we mean by linearity of the derivative. This is basically a statement of what we mean. So when we say that the derivative is linear, what we're really saying is if we take any linear combination of two differentiable univariate functions, which I'm calling f of x and g of x here, and we take two arbitrary constants, a and b, and then we take the derivative of the sum, a times f of x plus b times g of x. This is what's called a linear combination. That's where this name comes from. So we take the derivative of this weighted sum, and then we get what we expect. We get a times the derivative of f with respect to x times b times the derivative of g with respect to x. I'm using Leibniz's notation for the derivative here. You can also write this using Newton's notation, which I'm actually going to do later. So I think you should get used to seeing both forms of notation. But anyway, that's the statement of linearity. So that's ultimately what we're going to prove today. And like I said, corollaries. These are so before I actually prove the full linearity of the derivative, we might as well prove that if we assume that we do have linearity, which we are going to prove, that we get these two very simple corollaries. First corollary is called the addition rule. This just says if we take the derivative of a sum, we get the sum of the derivatives of the corresponding functions. This follows immediately from linearity if we let a and b both equal 1. I think you can see that. Derivative of 1 times f of x plus 1 times g of x is just 1 times df dx just plus 1 times gx. So that follows as long as we let a and b both equal 1. I think that's pretty easy to see. And corollary 2, scalar multiplication. And here I'm calling the scalar k. K is just a constant. It says the derivative of k times a function is just k times the derivative of that function. Well, this follows if we let a equal k and b equals 0. Here we only have one term in the sum. If you like, we kind of canceled out the second term by setting the constant multiplying it equal to 0. And we just changed the name of a to k. I didn't have to do that, but I kind of prefer using k for scalar multiple. I don't know why. You just kind of see it a lot. But anyway, those follow immediately. I think you guys can see that. And now, finally, all we have to do is prove linearity and its full generalization. So to do that, let's simplify things a bit first by letting capital F of x be little a times little f of x plus b times little g of x. I mean, that is the thing we want to calculate the derivative of. So we really want to calculate f prime, capital F prime of x, and show that that's equal to little a times little f prime of x plus little b times little g prime of x. If we can show that, then we're done, because that is just a statement of linearity of the derivative. So here we do it. I mean, we use a definition, the limit definition. And it's a little bit of a complicated derivation, but I think you can kind of follow it. So, the first line, I'm just applying the definition of the derivative of capital F. And now in the second line, I'm substituting what capital of F is. And remember, capital F of x is just a times little f plus b times little g. And so I do that on both sides. I mean, here we have capital F of x plus h. This is where things get a little messy, because we have to write x plus h instead of x, which I've done here. So we're going to get inside the limit. We're going to get little a times little f of x plus h plus little b times little g of x plus h. That is what capital F of x plus h is. Now we have to subtract capital of F of little x, which is just little a times little f of x minus little b times little g of x. And now in the third line, all I'm doing here is rearranging terms a little bit. Notice you can just switch the two terms in the middle. We're regrouping terms, basically. And I think you'll see why I'm doing this here, because now we're getting something we can actually apply the definition of derivative to. So notice on the left here, now we can split, once we've done line 3, we can do line 4, which is just splitting up this limit of a sum of two terms into the sum of two limits. You can always do that. The limit of u plus b is the same as the limit of u plus the limit of v. I think that's pretty easy to see. And so that's all I'm doing here. I mean, we're just splitting up the thing inside the brackets on the third line into two brackets. And now, okay, then the fifth line, we can also factor out constants from limits. It's pretty easy. You can do all this with limits. I mean, I'm not proving this here, but just from the definition of limit, I think it's pretty easy to see that this is true. If you want, you can kind of torture yourself and use the epsilon delta definition of limits to prove these facts, but they are true. Just trust me on that. But anyway, so if you assume all that, then the fifth line, we got a times the limit of f of x plus h minus f of x all over h. But notice that this limit now is nothing but the definition of the derivative of f. So that's f prime of x. So now on the sixth line, the first term is just a f prime of x by exactly the same reasonings. The term on the right is bg prime of x. And now we're done, because we proved what we wanted. We proved that capital F prime of x is equal to little a times little f prime of x plus little b times little g prime of x. In other words, we've proven that the derivative is linear for arbitrary differential univariate functions. So voila, that completes the proof, and that completes today's lesson. Thank you for watching. Long live math, and I'll see you guys next time. Bye.